Okay, moving on to automata theory. We're asked to design a finite state automaton that recognizes the language denoted by the following regular expression. So there's a few ways you could do this. You could either just try and design a DFA or an NFA from like intuition, based on what the language does, or you could directly take this regular expression and blindly convert it to an epsilon NFA using the algorithm. Either would work. So I'm just going to build a DFA for this question. So I have to reason about what sort of states am I going to need. Well, I guess I'm going to have a starting state, first off. And then I'm going to have to try and have another state. Well, a single A is bad, and I won't allow myself to transition on to future things. So I'll have a state that if I see an A, I go to S1, and if I read another A, I go back to S0. And then I can only move onwards from S0, so that ensures there has to be an even amount of A's, including no many A's. So AA, that's fine. And now I have to have at least one B. In fact, this language would be easier to translate if I wrote it like this instead. AA star, B, BB star. And these are the same regular expression, they generate the same language, because if this is all B's, it doesn't matter if the single B is on the back or on the front. So I can abuse that property to make it a bit easier. So read the single B, and then I can accept. Or I can decide to read as many evenly many B's as I want. So if I read a single B, I shouldn't accept. But if I read one more B, I start accepting again. Okay? And this seems to work. So from S0, I can read pairs of A's, as many as I want, and then a single B, and then pairs of B's, as many as I want. So this would be a valid automaton for the problem. And clearly, this is a NFA. And why is that? Because S1 doesn't have a transition for a B. So because the transition function isn't total, that would make this an NFA. So let's look at the other way to solve this by directly converting it to an epsilon NFA. So I have to build a machine to recognize A, which looks exactly like this, and then a machine that recognizes A, and then concatenate them together, which will look like this. Okay, and then I can do that whole process as many times as I want. So we have to do the star pattern. So I epsilon in and I epsilon out. And then I can choose to skip the whole thing. And once I've consumed two A's, I can choose to do that again as many times as I want. Okay, so that's my starting state. So this whole machine is basically AA star. And now I'm going to build a machine for BB star. Okay, so what's that going to look like? So it's basically the exact same machine again. So I'm just going to copy it because I'm lazy. Except we replace the A's with B's. Okay, and when we concatenate two machines, the states are going to overlap. So the final state of the first becomes the starting state of the second. And then all we've got to do is replace these characters here with B's. And the last thing is I have to accept one more B on the end. So I can read a B and only then accept. So that would be a epsilon NFA for the same problem. Which should you choose? Well, I guess it's up to you. For me, I found it easier just to design an NFA for this problem on the spot. But if you can't think of a way to do that, you could just blindly convert it to an epsilon NFA, and that would also be a totally valid approach. The other thing we have to do is describe in English the language that my finite state automaton accepts. Well, hopefully, if I've solved the problem correctly, the language it accepts is precisely this language. So how could I describe this language? Well, it looks like evenly many A's. So that is, pairs of A's are followed by what? Followed by evenly many B's and a single B. Well, evenly many B's plus one more is going to be odd many B's. So followed by odd many B's. You could also state it as like A to the N, B to the M, where N is even and M is odd. How else could you describe it? You could describe it as A is 2 to the N and B is 2 to the M plus 1, where N and M are just integers. Well, non-negative integers. I guess if they want a description in plain English, this would be probably what they were looking for. Okay? We're also asked to describe if my finite state automaton is deterministic or not. Well, I guess that depends on which one you build, right? Here I've built an NFA because the transition functions are total, And here I've built an epsilon NFA that's also not deterministic because it's got epsilon transitions. So that answer will obviously depend on what machine you come up with.